Hello there. Today we'll be covering more matrices and a special number associated with matrices called determinants. In the picture here, I drew a waffle cooking because, waffles look like matrices. You can think of a matrix as an n by m array of complex numbers, where n and m are positive integers. And matrices can be indexed by two numbers, as shown on the bottom right, aij, where I is the ith row and j represents the jth element in the ith row. And in the picture in the bottom left, I drew a representation of the matrix A using its index representation. A matrix is square if the number of rows equals the number of columns. In the last video, I defined matrix multiplication, and we will revisit it here. If a matrix C is A times B, then the ijth element of C equals the sum over k equals 1 to m of aik times bkj. This will only work if A is an n by m matrix and B is an n by p matrix, where n, m, and p are arbitrary positive integers. Otherwise, the matrix product or the matrix multiplication of two matrices is undefined. A more convenient way to write the sum on the left is Einstein summation notation. We could simply write Cij equals Aik times Bkj. And with Einstein summation notation, it is implied that all repeated indices are summed over all of its possible values, and the I and j from B carry over to the I and j in C. Here we will use more examples of Einstein summation notation. A dot product of two vectors, A mu times B mu, a dot product between two vectors A and B, it's just a sum over all of its indices, A mu times B mu. And the matrix vector product can be defined as AI equals Aij times Cj, where AI represents the indices, where I represents the indices of the resulting vector. And here, vector is, in this context, is defined as a column of numbers from AI all the way to A1 all the way to AN. And note that you can tell what the result of an Einstein summation would be based on the number of indices it has. For example, you can tell that the result of a dot product is a scalar because A has no indices. You can tell that AI is a vector for the matrix vector product because A has one index. If the element has two indices, then it'll be a matrix. For three or more indices, it is what is called a tensor, and a tensor is a multidimensional array of numbers. For the rest of this video series, I will use Einstein summation notation, as they can make writing out equations and doing derivations much, much easier. Here we will define an adjoint of matrix A. If a matrix B is the adjoint of matrix A, that means the ijth element of B equals the jith element of A's complex conjugate. In the case that A is real and B is called the transpose. A is an n by m matrix and B is an m by n matrix. Now, there are certain matrix definitions and properties that apply only to square matrices. A matrix is diagonal if all of its non-diagonal entries are 0. I drew an example on this page where we have A equals 1, 0, 0, 0, 2, 0, 0, 0, 3. And a trace is the sum of all the diagonal elements of a matrix. So the trace of A will just be 1 plus 2 plus 3, or 6. A special matrix called the unit or identity matrix is defined to be a matrix I, where I times any matrix equals A times any matrix equals the matrix itself. And I is just a matrix with all of its diagonal entries as 1 and all of its non-diagonal entries 0. and I drew a 3x3 version of the identity matrix on this page. The inverse of a matrix A is defined to be a to the negative 1 power. It is also a special matrix where a times a to the negative 1 times a equals a times a to the negative 1 equals the identity matrix. And note that all matrices, or not all matrices, are invertible. An example of a non-invertible matrix is matrix of all zeros, where, as you can see, no matter what you multiply this by, you can never force any of the elements in that matrix to be a 1. A unitary matrix A is a matrix where its inverse is adjoint, or a to the negative 1 equals a adjoint. And a real unitary matrix is also known as orthogonal. A Hermitian matrix is a matrix where its transpose equals itself, and a real and a Hermitian matrix is symmetric. Alright, now we will move on to determinants. A determinant is a special number that is associated with a square matrix. The definition of a 2x2 determinant is, for matrix A equals ABCD, is the determinant of A is AD minus BC. For a 3x3 matrix, the definition is A times the determinant of EFJK minus B times the determinant of DFIK plus C times the determinant of DEIJ. And notice that you can get the elements of the corresponding determinant by crossing out the row and column where the element is located. In general, for an n by n matrix A, the determinant of A is defined to be A11 times the corresponding determinant formed by the crossing out, as described in the previous page, minus A12 times the similar procedure, and so on, with alternating signs. And a few special properties of determinants are that if all the elements in a row or column of a matrix are 0, then the determinant of A is 0. If A is diagonal, then the determinant is just the product of all its diagonals. And if you exchange any two rows or any two columns of a matrix, it flips the sign of its determinant. And the determinant of a matrix is equal to the determinant of its adjoint times the complex conjugate of the determinant of its adjoint. And the determinant of the product of two matrices is the determinant of the first matrix times the determinant of the second matrix. Another way we can write the determinant of A is A with two solid vertical bars around it. It looks similar to an absolute value sign. An important thing to know about determinants is it could be used to test whether A is invertible or not. If the determinant of a matrix is 0, then that matrix is definitely not invertible. Else, we can be sure that it is invertible. Alright, that's all for this video. Have a great day.